So now Cerys Jenkins will present Learning from Faces and Favorite Toys, Effect of Domain and Classification Level on Robustness. Please give her a warm applause.
Good afternoon. Hope that works. Thank you all for being here today. I'm Cerys from the University of Edinburgh, and today I would like to present our paper on learning from faces and favorite toys, the effects of domain and classification level on robustness. And this was written by myself, Deepayan Sanyal, Joel Michelson, and Maithilee Kunda. So inspiration for this project first came about by looking at work in developmental psychology. During infancy, humans experience a natural period of blurred vision. So although this may seem like an early limitation, studies have found that in fact this is adaptive, enforcing a natural curriculum which can help infants to develop more robust visual processing strategies. Zhang and Tong went on to study this effect computationally by training a CNN on a blurry-to-clear curriculum similar to an infant's visual development. Specifically, they trained their CNN on two different datasets, a faces dataset and an object dataset. And they found that although faces were able to leverage from this blurry-to-clear curriculum in order to develop more robust representations, the same effect did not extend to objects. However, we examined an alternative hypothesis, and that is whether this effect extends to faces because they are an intrinsically instance-level task, whereas for most object-level studies are studied at the category level. So what is the difference between an instance and a category-level task? So here I've presented examples from a typical faces dataset and a typical object dataset. So the first row shows images of Angelina Jolie, and she's presented at different times, in different settings. She's looking at the camera from different angles. However, crucially, each of these images maps onto the same physical person in the real world. There's only one Angelina Jolie. In contrast, each of these images of elephants all map onto a different physical object in the real world. So in order to test our theory, we derived an instance-level object dataset in order to compare it to a category-level object dataset. We used Toybox, which was developed by Avis Lab at Vanderbilt University. So Toybox contains videos of 12 different categories of toys undergoing handheld manipulations in both structured and unstructured manners. It was designed to better mimic an infant's visual development when compared to the typical large-scale object datasets such as ImageNet. We created two splits of the dataset, an instance-level split and a category-level split. So the instance-level split contains 360 classes, where each class contains images which map onto the same physical object. In contrast, the category-level split is just the standard Toybox dataset, which contains 12 different classes, where each class contains 30 individual objects. To serve as controls, we also trained our CNNs on 3 additional datasets. So our first is a faces dataset, and this contains classes of approximately 300 celebrities taken from the Face Scrub database. And then we use 2 versions of ImageNet. ImageNet 12, which is a category-matched dataset to Toybox, so it contains the same 12 categories, but of real-world objects. And then we used ImageNet 100, which is just a subset of the wider ImageNet 1000, containing 100 randomly sampled classes. In order to test our hypothesis, we use CNNs. CNNs provide an ideal architecture for studying visual development because they have many properties that mirror biological vision. So for example, they have a hierarchical architecture that mirrors the ventral visual cortex, and they also are able to produce human levels of accuracy. Notably, CNNs have been shown to produce brain-like responses when trained on developmentally realistic inputs, suggesting that both learning systems respond in similar ways to problem structures and constraints. Specifically, we used an AlexNet architecture, which provides good accuracy whilst remaining computationally efficient. We trained our CNNs using a blurry-to-clear curriculum, similar to the one used by Zhang and Tong. So we began training by applying a Gaussian blur with a standard deviation of 8 to all of our images. And then we subsequently reduced the blur level by a factor of 2 every 20 epochs, such that by the final stage of training, our CNNs were exposed to clear images. Additionally, we trained separate CNNs on clear-only images and blurry-only images to serve as controls. And all of our CNNs were trained for a total of 100 epochs. After training our models, we tested them on images by applying different levels of blur to the test images. And we found that, in line with our hypothesis, CNNs trained on instance-level dataset were able to leverage from this blurry-to-clear curriculum in order to develop more robust representations than their clear-only counterparts. So they developed a higher accuracy ratio. In contrast, the 3 CNNs trained on object-level tasks were not able to see this same level of difference in accuracy ratio, whether or not they were trained using the blurry-to-clear curriculum. Importantly, we found that this performance gap cannot be solely attributed to training duration, since for ImageNet 12 and Toybox category level, when they were trained for a shorter period, they still were not able to see the same accuracy ratio as faces. And for Toybox instance level, although it was trained for a longer training duration, it was able to maintain higher levels of accuracy ratios. In addition to looking at performance accuracy, we also examined the receptive field sizes that our models developed throughout training. And this revealed some really important differences between faces and objects. So here you can see that for blurry-to-clear training, for our 2 instance-level datasets, the receptive field sizes increased slightly, whereas for the 3 category-level datasets, they remained fairly stable or decreased a little bit. Then for the blurry-only condition, we see fairly similar results across all datasets, where the receptive field sizes remain fairly stable. But the interesting difference comes from looking at the clear-only trained models, because for all of our object-level datasets, CNNs trained on clear images developed much smaller receptive field sizes. However, in contrast, for faces, our CNNs developed unusually large receptive field sizes. And so this suggests that the content of face images alone is enough to encourage CNNs to expand their receptive field sizes and integrate more wider spatial context. So, in conclusion, we find that instance-level experiences are important for the development of robust visual strategies. And in fact, this mirrors an infant's visual development, because as infants, we have many instance-level experiences, whether that's seeing your mother's face every day or playing with the same favorite toy repeatedly. And so we suggest that these instance-level experiences lay the foundation for later robust categorization. Standard CNN training typically bypasses this instance-level learning phase because it's often seen as an easy problem. However, we suggest that future computer vision models should integrate both instance and category level information in order to develop human levels of robustness. Finally, in line with findings from Zhang and Tong, we find that there does appear to be something special about faces that goes beyond them simply being an instance-level task. So although the greater robustness shown by the faces model could be due to differences in dataset variety, where our faces dataset was much more varied than our Toybox instance-level dataset, the fact that faces cause CNNs to expand their receptive field sizes suggests that they may benefit from both domain general instance learning strategies and domain-specific processing. And this is an evolutionarily plausible hypothesis given the social significance of faces. It also aligns with neural evidence, which suggests that there are regions of the brain which are specialized towards processing faces, such as the fusiform face area. Thank you for listening.
Thank you very much. I already see a question over there, and another one here.
Yes, thank you. Those blurry pictures that you showed at the beginning, they are often to be found in standard developmental psychology textbooks, but they're not really very truthful for neonatal perception or vision. We now know that babies, neonates even, they focus perfectly at 20 centimeters, which is exactly the length of their arms and their mother's face when they're being fed. So nature has made it such that neonatal vision is perfect for the things that they need to see, namely their mother's faces and their own arms, to be able to start eye-hand coordination. So, yeah, I think you may have started from the wrong starting point.
Yeah, I see what you're saying. And I realize that, so a lot of our experiments, we try to focus more on applying the concepts rather than mapping the exact learning periods, because also I think, so infants' development of their vision progresses much more quickly than when they start picking up objects, for example. So it's more just sort of, rather than mapping the phases on a timeline directly, it's more just kind of taking the concept and applying it to a CNN and seeing if we can see any benefits. I guess the first inspiration for this project came from looking at a paper by Vogelsang et al., and it looked at infants with cataracts. And they found some really interesting effects with infants who were treated for cataracts. So they had a starting point of much more clear vision than their normally developing counterparts. And they found that they weren't able to develop the same processing strategies. So I think even though infants' vision is optimized for what they're meant to be doing, there does seem to be something interesting about how their visual acuity develops that supports this learning process. But that is a good point.
There was a question already. Maybe you can have a...
Hello, thank you so much for the presentation. What I'd like to ask is that, have you tried this CNN training with a data set which is a mix of blurred images and regular images at the same time? Because in your current regime, first there are blurred images, then there are actual images, and blur is a way of augmenting the data set. So the effects you are describing as an outcome of your research might be because of just data augmentation rather than the biological mirroring that you're proposing.
No, we haven't tested that in our data sets, and there are like a lot of CNNs that are trained using by applying blur augmentation to some of the images, and actually I suggest that this is reflective of humans, because I mean, even in everyday life now we see lots of instances of blurry images, and we're able to recognize that. But I guess what I'm suggesting here is that by using this blurry-to-clear curriculum, after the final stage of training, so in test, we should be able to recognize both clear and blurry images. So kind of leverage from this curriculum to recognize both types of images. But that's definitely something that we could go on to test in the future by just, instead of using this learning curriculum, applying blur augmentation from the start to some of the images.
Thank you.
There's a quick question.
I mean, it's sort of a follow-up of the comment that was made before, that during development it's not only a problem of accommodation, it's also a problem of spatial resolution, which changes during development. So you should also take into account the fact that the retina is not a constant resolution device, and there are also eye movements involved in the recognition process, which is a very interesting aspect from the robotics point of view.
Yeah, that is also a very good point, and one for further investigation.
Thank you. Thank you again.